Hello one and all, today we are tackling a medium challenge problem on HackerRank called highest value palindrome. As typical, I will go over the problem, give you some time to do it on your own, and then go over my solution. Palindromes are strings that read the same from left to right or right from left. For example, madam or 0110. You will be given a string representation of a number and a maximum number of changes you can make. Alter the string one digit at a time to create the string representation of the largest number possible, given the limit of the number of changes. The length of the string cannot be altered, and you must consider zeros on the left of all higher digits in your test. So for example, 0110 is valid, but 0011 is not. Given a string representing the starting number and a maximum number of changes allowed, create the largest palindromic string of digits possible, or the string -1 if it is not possible to create a palindrome under the constraints. For example, given the string 1231, and the k, or the number of alterations, set to 3, you can replace the ones on the end with 9s, and you can replace the 2 with a 3 to get 9339. Another example is given the string 12321 and the number of alterations set to 1, you can replace the center 3 with a 9 to get the largest number of 12921. So that's the challenge. I'll give you some time to do it on your own, and I will come back with my solution. Good luck. So here, the approach is we're going to want to have as many 9s on the left as possible, but because of that, you also have to put it on the right because it's a palindrome. And what we can do is use any surplus alterations available. And by that, I mean we have to kind of keep track of two things: the number of mismatches, which are kind of a requirement that we have to change. We have to use alterations to change those, but at the same time, whatever surplus we have, we can use to kind of just squeeze in 9s at the end, which will optimize the largest number. So let's see what an implementation of this algorithm would look like. First, you're going to need to take your palindrome, the string that you're given, which I guess won't necessarily be a palindrome. You need to kind of break it up into its parts. You need to get the left, the right, and if there's a middle, kind of they handle it by itself. And what we'll want to do is just go once through and just keep track of any mismatches, just to keep track of the number of mismatches. Once you have that, you essentially have like a lower and upper bound. The lower bound being the number of mismatches, which you have to fulfill, versus the k alterations, which is like the potential surplus that you can use for kind of filling in as many 9s as you want. Then we're going to create a string as the output for the palindrome, and then we're just going to loop through our left and right characters of the string that we've just parsed, and we're going to go outer to inner. So on the outer part, we're going to try and squeeze as many 9s as we can, because that'll count for the inner as well. And if we don't have a mismatch, that's great. That means that we have an opportunity here to squeeze in 9s and just change both of those to 9s. If we don't have a surplus, then we can just ignore it and just keep them as is, because they're already a palindrome essentially. If we encounter a mismatch, then we have to kind of consider a few things here. First, if one of those numbers is already a 9, then your job is kind of half done, right? You just need to convert the other one to a 9, in which case you're only spending, one alteration. If both of those numbers are not a 9, then you have to kind of tease this out a little bit. The first thing to consider is how many alterations do you have available. If you have 2 available, then you could just spend those 2 to change both numbers to a 9, and you have that's totally valid. Or if you only have 1, then you can just change one of those, the smallest one, to the larger one, and you spend 1 alteration doing that. Okay, so for my first example here, this is the problem that they give us. I broke it up into a few parts here. So on the left here is kind of like the expectation. We are given k of 1, input of 394, and the expected output is 3993. We're changing the 4 to a 9 essentially. And what I'm doing here is kind of breaking the algorithm down into its separate parts here. First, we break the input into the palindrome parts. So we have a left side. I'm going to zoom in, maybe that'll be a little easier. So there's a left side here, a middle, which there is none because it's an even number, and a right side. And what we're going to do here is take those parts and basically line them up as if they were kind of like in the palindrome form, but we need to like flip the right side to be reversed so that they kind of line up. So here I have the left side and the right side basically right next to each other, kind of zipped up next to each other, if you will. And the right side is just reversed so that they are kind of in line. So now that they're lined up, we can count how many mismatches they are very easily. So I know visually we can see easily that there's only one, but we could also programmatically approach this by just like kind of looping through both and just counting which ones are mismatched. So here we have a mismatch count of 1. So now our algorithm will kick in. We're going to go one at a time, outer to inner, which means kind of just like 3, then this 9, 4, and then we're done basically. So the 3s are a match. We check, okay, we have a match, but is there a chance to turn these into 9s? And the answer is no, because we have K currently at 1. What also we need to keep in mind is we have also mismatches, which we have to reserve. So we actually have to reserve 1K just for that to be handled. So we don't have the chance to do it here. So we just carry the 3 over into our output string. This output string will be basically the left side of our palindrome. I don't need to keep both sides because a palindrome is a palindrome. So as long as I construct one side, I can just like flip it and make the other side. That's why I only need to really create one side for our output. Okay, so after we're done with the 3, we go to the next iteration and we go to the 9, 4. So here we do have a mismatch, and we'll go and check, okay, is there a chance for us to turn these into 2 9s? Fortunately, one of them is already a 9. So we are basically just asking, can we turn this 4 into a 9? We look at our Ks. We say, hey, yep, there's a K available. We can turn that to 0. We'll also have to decrement our mismatches left because we were solving one of those mismatches. And we're going to turn that into a 9 essentially. And this will become a 9, and I'll be turning that into a 9 here. So our output side will be 3, 9. And now all we have to do is like reconstruct our output. We'll put in a 3, 9 here. We'll take our middle that was over here, which is nothing, so we don't have to do anything there. And the reverse output, which is now going backwards, is 9, 3. So we'll put 9, 3 here. And that is the expected output. And that's how we work through the algorithm. So here is a slightly longer example. We're given a K of 2, input of 9, 3, 2, 2, 3, 9. Hey, it's already a palindrome. And so the output is expected to be 9, 9, 2, 2, 9, 9. And so let's see how we'd go through that. So first we will break our input into the palindrome parts, the left side, middle, and right side. There is no middle, so that's easy. We'll take our right side and kind of flip it so that it lines up with our left side. And so we see that everything's basically lined up. We have 2 9s, 2 3s, 2 2. So everything's already a palindrome. But here's where we get the opportunity to turn our surplus into a larger number. So we're going to iterate one at a time here. We're going to see the 9s first, and we would want these to be 9s, so we can't really make those any larger. So the first output side is going to be a 9. Then we'll go to the 3, and sure enough, the 3s, we would want those to be 9s as well. And we need to ask, hey, is there any surplus left over? And the thing is, if we take our mismatches into account, along with our alteration amount, we can say 2 minus 0, and we basically still have 2 left over. So we know that we can use those surplus to change the K while still having whatever is left over for the mismatches. In this case, we can do that. So we would take, so what we would do is change these 2 3s into a 9. And then we would decrement the K by 2. So their K is 0 at this point. Now we'll go to 2s, and we see, well, the 2s are there. We want those to be 9s, but we don't have any alterations left, so we can't do anything. And they're not a mismatch, so it's just fine to keep that as is. So we'll have a 2 here, and then sure enough, we'll fill these in. And sure enough, we get our answer as expected. So here we have essentially the exact same problem, except our K is equal to 200. So we have plenty of alterations. We can just change everything we want, essentially. So there's really not much difficulty here because we have so much surplus that we can just change literally everything to a 9. Whether or not it's even a mismatch, we can just change it to a 9, right? So in this case, it's pretty simple here. We would check the 9s here. They're already 9, so that's kind of already spent. We would check the 3s and say, okay, we can use 2 of these surplus, so that would come down to 198. Turn that into a 9 essentially. Both those get to be put to a 9. Then we go to the 2s and say, hey, we have plenty of surplus. We're going to subtract 2 from this and then make that also a 9. And sure enough, everything just becomes 9s, 9s, 9s. So everything becomes 9s. It's super easy. Okay, so we'll go through this and we'll see that we want to first loop through it to see how many mismatches there are. So if we go through it, we'll see our count of mismatches is actually 2. So we'll make sure to have that. So now that we have our mismatches set to 2, let's go through and iterate through this. So here we would look at the 0 and the 3, and we know, hey, that's a mismatch. Can we turn these into 9s? We don't really have the surplus to do that. The reason is, if you could imagine the world where we fix this iteration and we don't have a mismatch, we would subtract this by 1, right? Meaning we would still have one mismatch left to deal with, so we don't have the surplus to subtract 2 from here, right? If we take this to 2, then we don't have enough left to handle that one mismatch. So with that forethought in mind, we know that we can not take out 2, but we can take out 1. And what I mean by that is we can use that 1 to turn the 0 into a 3. Okay, now I'm not going to do that here. I'm going to do it here, but that's the idea. We have to just use the bare minimum number of alterations to handle this mismatch. In this case, turning the 0 into a 3. And then we would take our mismatches and reduce that by 1 because we just solved one mismatch. And then we go to the second iteration. Same thing basically happens here. We don't have enough to change both to a 9, but we can still handle a mismatch with 1 alteration. So that's one thing to keep in mind. As long as you have 1 alteration, you always have the ability to handle and solve 1 mismatch. So that's why it's like kind of the bare minimum here. So once I look at this, I say, hey, I have 1 change available. I'll turn this into a 2. So that becomes that. And then we have 0 alterations and 0 mismatches. Then our output becomes 3, 2. Oops. Our middle, well, our middle needs to kind of be considered here as well. The thing is, the middle basically doesn't change unless you have any remaining alterations. There are none, so our 1 just gets basically carried down from its original position. And then the reverse of our output is 2, 3. So our output will become 3, 2. That is exactly what we expected to see here. So the next problem is actually the same one, except the K is 3. So let's see what that looks like. So we go through the same thing. We basically do our mismatch count, and we notice, oh, this is also 2. So that's something to start off with. And we go through the first iteration. We see a 0 and a 3. And we check, hey, in the world where we solve this mismatch, this would become a 1. And the K's, if we could subtract 2, would there be enough for those mismatches to be handled? The answer is yes. So in that world, we can turn both of these to a 9 safely. So that's exactly what we're going to do. We're going to take these and make these a 9. And then we go to the next iteration and we say, okay, is there enough to make those both a 9? The answer is no, but we still have 1 alteration because we make sure to keep those, we make sure to save those. And so we will have enough to just change the 0 to a 2, but you still, solve a mismatch. So that becomes a 2. Sorry, let me correct this. So this becomes a 0, this becomes a 0. So we're now done with our iteration here. We then try and fill up our opposite side here to be a 9, 2. Now our middle is in the same boat as before. There are no alterations left over, so we just kind of carry it down. And so this output is a little bit different. Even just adding that 1 little alteration allows us to significantly change the value of the output. We get 9, 2, 1, 2, 9. When do we actually ever change the middle, right? So that's the question. So in this situation, this is the one time we can do that. So here we have an input of all zeros, 5 zeros. So we do have a middle value, and we have K equals to 1. So we parse those out, and we find that we have 0 mismatches, but we don't have enough K's to change 2 things into a 9. So if we go through our iteration, we'll see, okay, 2 zeros, can I have 2 9s? The answer is no, and that's always going to be the case. So our output will just be 0, 0 here. And so we carry that over here. So now when we consider our middle, we look to it and say, okay, do we make you a 9 basically? And the answer is yes, we have surplus here. So then we would say, okay, we can decrement that by 1. Not that we're going to use it anymore, but we do have 1 left over. Instead of a 0, we now make that a 9. And then the reverse of the other side is 0. So here we have the largest number you can make out of that situation. All right, so let's look at the code and see what we can do here. So first, I will have 2 helper functions set up for this. I will first have a count mismatches function, which will take 2 strings and just count the number of mismatches between them. At first, I will assert that the length is the same because that is a requirement here. Otherwise, I'll just take a running count, loop through both. Here I'm like zipping it, but basically if any character is not the same as the other, I will just add that to the count and return the count. That's all. Next, I will have my parse palindrome parts function. It takes a string and it will parse the string into its palindrome parts, the left, the middle, and the right side. The right side is going to be reversed just so that it lines up with the left side, but that's kind of it. I'll go quickly over the logic here. First, I'll check to see if there's an odd number for the length, and if there is, then it has a middle. So that'll be true if that is a odd number length. Then I'll parse out what the center index is. This is using this floor division basically. So if there's a remainder like 5 divided by 2, then I just want the 2 essentially. So it removes the decimal and allows you to get an index that you can actually index with. And the reason for that is because even if you have an odd number, the 2 is still the middle value essentially if the length is 5. So The left part, we grab basically everything up to, but not including the center index. Then we can take the middle. If there is a middle, we will grab it out of the string. Otherwise, I just want to make an empty string for that because there is no middle essentially for that. Then the right part is, again, a little contingent on whether there's a middle or not. So if there is a middle, then I want to grab the 1 plus the center index because I want to skip the center and grab the right part. Otherwise, there is no middle and I can just grab the center index onward. And so that's how that works. And then I will return the left part, the middle, and then the right part, but the right part is reversed in order to, again, line it up with the left part. All right, going into the main function here, just a quick stipulation here. I got sick of typing the string 9, so I just made a variable 9 because I like doing that kind of thing, I guess. Anyway, highest value palindrome function takes s, n, and k. S is the string, n is the length of the string, and k is the number of alterations we have available. Here I'm calling my parse palindrome parts, PPP. Nice alliteration for you. I'm parsing it out and getting the left, middle, and the right reverse part. Then I will use my other function, the count mismatches, to grab the left part and the right reverse part and see how many mismatches there are. So this will be a number of the number of mismatches. So here I have a bit of a shortcut going on just because we have a situation that bears a little consideration. What if you have a very large k and in fact your k is much larger or even equal to the length of the string? Then you could just alter everything to be a 9, and that's essentially a very easy way of just giving a quick answer if that's the situation. A string that's of the same length as the input and just all 9s essentially. All right, so the other shortcut situation is when you don't have enough alterations to handle the number of mismatches. So if you subtract mismatches from k and that's less than 0, that means you don't have enough alterations to handle all the mismatches. Like you need at least 1 per mismatch. So if that's the case, then you know definitively you do not have enough to handle the mismatches. You can return 1 at that point. So once we get past these two like guard statements, these are going to return, right? So once we get past these two, we know for sure that we have enough alterations to handle all of our mismatches. Now it's just a challenge of figuring out where we can optimize to insert as many 9s as we can in the right places. So here is where we begin. We're going to start a final left empty string. This is going to be the left side of our final palindrome. I don't need to keep the right part because it's a palindrome, so I'll just take the same left side and just reverse it, and that'll be the right side. So that's why I'm doing it that way. Then we're going to iterate through both of those strings, the left part and the right reverse part. Here I have it zipped up so that they kind of go at the same time, and I have the left character and right character at this point. But we're going from the outer part to the inner part. So as soon as possible, we want to use any surplus alterations to insert 9s. All right, so here we'll go. We'll have a Boolean here is mismatch. It just returns true if the values are not the same. If they are the same, then it's not a mismatch. Then I want to do something where I'm basically counting the number of non-9 characters. I know that the word is a little kind of odd wording here, but basically, if there is a 9 already in place, I don't want to have to deal with it because it's already the thing I want. We want all the 9s, right? So what I want is how many things are not 9. That's the idea. And between the left and right character, if there's 1 or 2 or 0, that's worth considering. Okay, so what I have here is the next character, which I'm setting to none. This is going to be the next character that will be added at the end to the final left string. But our logic will determine what that value actually is. All right, let's get into the main logic here. So we're moving outer to inner here. So if the first value we're seeing is not a mismatch, then as soon as possible, we want to make those 9s with the surplus, right? So here is an opportunity. And by default here, I'm going to just set the next character to the left character. Because it's not a mismatch, that means that it is a match, basically. That means it's the same as the right character. It's the same number, right? As a default, we'll have that set up. But if we have an opportunity to use some extra alterations, then we'll change that to a 9. So first we need to say, hey, are both of these characters a 9? If they're not already a 9, then that's something we want to consider. If they're both 9 already, then we can kind of ignore it, right? Because the left character is already a 9, so we don't need to do anything. Then we can say, okay, well, what about the surplus alterations? What counts as a surplus? Well, because these are both the same number and they're not 9, we need to make 2 alterations to make this a 9. If we were to subtract 2 from the number of alterations we have, would there still be enough alterations to handle the number of mismatches that we have? The answer is yes. Then we have the surplus to do this. Then we can change these to 9s. We'll subtract 2 from the alterations and make the next character a 9. Okay, the next situation is, well, if it's not a mismatch, then it is a mismatch. So here's where we handle mismatches. So again, we're still going with the logic that we want to replace as many of these with 9s as possible. The first situation to consider is if one of those characters is already a 9, because your job's already kind of half done in that case, then we can use the 1 alteration. And keep in mind, we have set up the logic in such a way that we have ensured that there's always at least 1 alteration available for every mismatch. So here we're just using the 1 that we have reserved for this mismatch. So first we'll check, hey, is one of those values a 9? If it is, then we can just use 1 alteration, -1. We solve 1 mismatch, -1 on that, and then we can change the character to 9 because they're both going to be 9. And that's that situation. Otherwise, both characters are not 9. So here's where we have to kind of consider, do we use 2 alterations to make them both 9? Or if there's not enough available, then we just use the minimum 1 alteration that we have reserved for each mismatch. Do we use that 1 to just convert the lower number to the higher number? That's basically what we're trying to decide here. So that's what we're doing with this logic. So here we would ask, okay, if we were to reduce the number of alterations by 2, will there be enough to cover the mismatches after we've solved this mismatch? So we have to do a -1 here. But basically, is there enough available for making both of these a 9? If the answer is yes to that, then we can use 2 alterations. So we -2 there. We subtract 1 mismatch because we're solving a mismatch, and the next character is a 9 because we've converted both into a 9. Otherwise, the else statement here is, well, we don't have 2 available. That means we have to do basically the last ditch effort. We use the 1 alteration that we have available. Again, we've reserved 1 alteration for each mismatch at this point, so we know we have 1 available. Then we'll just use the larger number and replace the smaller number with it. The way I'm doing that is to take the left character and the right character, turn those into ints, and take the max of those. Then I'll have the larger number as an integer, and I will set the next character to the string of that particular number. We decrement alterations by 1, mismatches by 1. So you'll notice that at this point, there's a little bit of redundancy. So there's definitely some efficiency that you can put in here, by the way. Like the whole mismatch -1 is always the case after this statement. So why put it in 3 different places, right? I'm doing this explicitly so that it can be really clear what's happening. You can definitely optimize this. There's a bit of like redundant logic going on here, yes, and I know that, okay, but I'm hopefully making this explanation as clear as possible so it's understood like what's going on. Once you have a good understanding, make it as efficient as you want, please. I implore you to do that. So once we're done with our logic here, we will have defined a proper next character to add to our final left part of our palindrome, and we will do that. Then we're going to be done with the full for loop here, and then we will now have to do one quick step, which is to determine what we do with the middle value, if there even is one. So if there are alterations still available, and if there is a middle part, then just take the middle part and make it a 9. You're using whatever surplus alterations to make it a 9. Otherwise, the middle part just stays whatever it is. It could be blank, it could be a number, it doesn't really matter. You're just like using whatever's there. And so here we are constructing our string. We take the final left plus our middle part plus the left part, but this time reversed. And that is essentially our right part, and that is what we return. So let's run some code. Looks good. Let's submit some code. Ooh, awesome. So let's do a little big O notation here. I think that parsing the palindrome parts, and because of the string, I believe you do technically go through each part of that. So I believe this is big O of n, because how you parse a string, because a string literal, you do need to actually, under the hood, it's actually going through and parsing it out and like grabbing those. So I believe that is big O of n. Count the mismatches. We definitely go one at a time through those, and so that is big O of n, but like divided by 2 technically, but it's a constant, so you still reduce it to big O of n essentially. It's still determined, the time complexity is still determined by n. This is all constant, it's just returning values. This is all just like math and returning values. Here we are looping through the left and right part, so this is another like big O of n minus 2, or sorry, n divided by 2, but still it's big O of n here. Math, just all logic. There's no other stuff going on here. It's just a lot of logic. So Yeah, I think this might be a minor thing, but it's not worth considering really. So I think I would reduce this to say, you know, total time complexity is set to big O of n, and that is basically it. It's like n plus n times 3 basically, which equals big O of n. All right, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time. Take care.